Assalamualaikum warahmatullahi wabarakatuh. So today we are going to enter chapter 6 EM Applications. So these are the table of contents. So we are going to have the introduction, of the application for EM, and then followed by Faraday's law, transformer, EM generator, and EM potentials. So we have for electrostatic to find the electric flux and also the electric field intensity. And for magnetostatic, we have the B, which is the magnetic flux and also the magnetic field. So Michael Faraday's hypothesis saying that if a current can produce a magnetic field should produce a current in a wire. Magnetic fields can produce an electric current in a closed loop, but only if the magnetic flux linking the surface area of the loop changes with time. So here we have a galvanometer. So galvanometer is a meter which shows the presence of a current in a circuit. So at this moment, we have not switched on the battery yet. So when we started to produce an electric current, when you switch on the battery, so the galvanometer will detect the sudden increase in the magnetic field, which will make the needle of the galvanometer to move to the right. So when the flux is constant, there would be no current detected by the galvanometer, so the needle will move on to the initial position. And when you switch off the battery, meaning that the current has stopped, so the galvanometer will detect the sudden decrease in the magnetic field, which makes the needle move to the left, which is on the opposite direction. And after some time, the needle will started to move to its original position, and this is what we know as the electromotive force, which is EMF, denoted by VEMF. This process is known as the electromagnetic induction. Faraday's law. So Faraday's law stated that a changing magnetic flux through a surface induces an electromotive force in any boundary path of that surface. So the magnetic flux, denoted by phi here, passing through the loop is actually the equation over here, the first equation. So flux is equal to the integration of the magnetic flux in a surface, through a surface, so with respect to the surface. So flux is measured in Weber. And then if the question asks you to find the EMF induced in a closed conducting loop of n turns, so n is the number of turns for the coil over here. So it is given by this equation. So VEMF is actually equal to minus n. So n is the number of turns. D over dt of the magnetic flux. So this would give minus n d over dt, the integration of the magnetic flux B with respect to the surface. A time-varying magnetic field linking a stationary loop, so the induced EMF is called the transformer EMF, a time-varying magnetic field in a stationary loop. So this is VEMF, which is denoted by VEMF and TR on top. This is transformer. But when it is a moving loop, not stationary, moving loop with a time varying area in a static field, the induced EMF is called a motional EMF, which is denoted by VEMF and M on top. So the total VEMF is actually the combination of the transformer EMF, okay, and also the motional EMF. A stationary single-turn conducting circular loop with contour C and surface S, so this is the surface, okay, and the magnetic field is passing through it, okay, in a time-varying magnetic field B. So the general expression of the EMF, so this is the one that we have earlier, okay, the one that I have highlighted with the red box. So VMF is equal to minus N d over dt, the integration of the magnetic field, the magnetic flux, which is B, with respect to surface. Okay, but if it is stationary, d over dt operates on bt only because it is stationary. So this is known as the VMF of the transformer. Okay. So the VEMF of the transformer, so the transformer EMF is actually the voltage difference across the small opening between the terminal 1 and also terminal 2. So this one, so VEMF of the transformer EMF is actually the voltage difference between terminal 1 and terminal 2. Okay, so that's why we have transformer EMF is equal to V1 minus V2. So if the loop has an internal resistance Ri, okay, in the previous example, we are not taking into account the Ri over here at the loop. But if you are going to add the Ri, okay, if you are taking into account an internal resistance at the loop over here, so the circuit can be represented by the equivalent circuit in B. So that's why you're going to have Ri, which is the internal resistance at the loop. So this is the terminal 1 and terminal 2. So you have terminal 1 and terminal 2 over here, and also the resistance, okay, they are not, so you have R over here and R over here, and then the transformer EMF would be after the terminal 1 and also terminal 2, which is situated here. Now the circuit can be represented by the equivalent circuit in B, which is this one. So current would be equal to VEMF of the transformer, or the transformer EMF, is equal to R plus Ri. So the addition of both resistance. Okay, Lenz's law is used to find out the polarity of the EMF transformer, which is the direction of I. Okay, so we are trying to show the relationship between the direction of I, whether it is positive or minus, with respect to the VMF. So the current in the loop is always in such a direction as to oppose the change of the magnetic flux that produce it. Let us look into the example here. So example 4.1. An inductor is formed by winding N turns of a thin conducting wire into a circular loop of radius A. So this is the radius. Okay, so the inductor loop is in the XY plane with its center at the origin. Alright, and it is connected to a resistor R as shown in figure below. So this is the resistor. In the presence of a magnetic field given by, so the magnetic field is going this way. It is given by this equation, B naught 2y hat plus 3s hat sine omega t, where omega is the angular frequency. See, Find A, the magnetic flux linking a single turn of the inductor. And then B, the transformer EMF or VEMF TR. Given that, okay, so you're given the N, the B, the A, and also the omega. So the values are given, so we're just going to plug in those values into the equation later. So A, the magnetic flux linking a single turn of the inductor. So this is the equation for the magnetic flux, which is equal to the integration of B with respect to ds, the surface. Okay. So what you have to do is just plug in the value of B. So you have B naught 2y hat plus z hat 3, okay, and then sine omega t dot with ds z hat, and then apply integration, and finally you have the answer is given 3 pi a squared B naught sine omega t. Okay. For the next question B, so the transformer EMF, which is VEMF, given that, okay, so you have all these values, okay, so VMF is equal to minus N d over dt of your flux is equal to minus N d over dt, the integration of B dot ds. Okay, so this is in the previous slide. I have already highlighted it. Okay, so we have already found out what the magnetic flux is from question A. So just plug in those values. Okay, here, so you have minus N d over dt. So this value we have already calculated, which is equal to 3 pi a squared B naught sine omega t. Alright. So you have to differentiate the t, so d over dt. So just differentiate d over dt over here. So you will have minus 3 n pi a squared. So now you have B naught cos omega t. So sine have become cos. Okay. So now plug in all the values of n, okay, of B naught, of A, and also omega. Alright. And you will have the answer, the final answer is equal to minus 188.5 cos 10 to the power of 3t. So that would be the VEMF, which is in volt. Okay, next we have transformer. So transformer is an AC device that transforms the voltage, the currents, and the impedance between two circuits through electromagnetic induction. So here you have two coils. Okay, so the first one over here, and then another one over here. So here at the first part, the first coil, so we have V1 is equal to minus N1 d over dt of the flux. Okay, is equal to minus N1 the integration of d over dt of B with respect to the surface. Okay, and then you will also have V2. So V2 would be equal to minus N2 d over dt of the flux, which is equal to minus N2 the integration of d over dt of B with respect to the surface. So from these two equations, you are going to have the ratio V1 over V2 is actually equal to N1 over N2. So for ideal transformers, your P should be equal the same. Okay, so P1 over here should equal to P2 at this part. So we have P is equal to IV, so P1 is equal to I1 V1 and P2 is equal to I2 V2. So in the end, we have the ratio of I1 over I2 equal to N2 over N1. Next, we have the electromagnetic generator. So the first one is the AC motor. So as you can see here, this is actually a permanent magnet. Okay, so you have the north pole and also the south pole, which is used to produce a static magnetic field, and the current is passed through the conducting loop. So the conducting loop would be here between the north and also the south pole. So as the direction of the current in segment 1, 2, so segment 1, 2 have a different direction. It is the opposite direction of the current at segment 3 and 4. Okay, so you can see that the arrows is the opposite direction. So the induced magnetic forces of the two segments are also the opposite. So this will induce a torque that causes the loop over here to rotate. So it becomes a motor. Alright, so in a motor, electrical energy supplied via a voltage source is converted into mechanical energy. So you can convert the electrical energy into mechanical energy. So this is called a motor. So for AC generator, it is the opposite one. Okay, so the process is the same, but for generator, the mechanical energy is converted into electrical energy. Okay, finally, we have the electromagnetic potential. So in electromagnetic potential, you are required to find out two things. So the first one, how to find out the electrical scalar potential, or V. So this is in volt. And how to find out the vector magnetic potential, which is denoted by A. So this is measured in volt as well. So in order to find electric scalar potential, so you have to use equation 1 over here. So E is equal to minus del V. So you have to know how to calculate using this formula. Okay, and then if you want to find out the vector magnetic potential, so you have to use the curl equation. So B is equal to del cross A, or the curl of A. So question will be asked like this. So these are the example of the questions for electromagnetic potential. So given that the electric potential is V is equal to 5x squared y squared plus 8xyz, so it is in volt. Find the electric field intensity E. So you're going to use the first equation, this one. So E is equal to minus del V. So just apply the equation for this one, plug in those values inside here, and apply your divergence. Okay, and then for question number 2, given that the vector magnetic potential is A, which is equal to 5 cos pi y x hat plus 2 plus sine pi x z hat in Weber per meter, and the question asks find the magnetic flux density B. So B is equal to the curl of A. So to summarize the Maxwell equation, so we have the table here. So D is equal to the permittivity of the electric field, and B, magnetic flux, is equal to the permeability times with the magnetic field. So here, Gauss's law, we use to find out the differential form and integral form of your E and also B. So you have to apply your divergence theorem over here in order to find E and also B. And then we use the Faraday's law to find out the curl of E. Okay, and also Ampere's law to find out the curl of H.